Today we're looking at another of the problems from your homework set, and this problem is not actually so difficult of a problem, but I'm going to make it a little bit more difficult. The reason that I'm going to do that is not just to make your lives harder, but to make sure that some common misconceptions aren't perpetuated. So right here we have a guy who pushes a box across the table, and specifically the question says, how far will it go after the pusher stops pushing, given that the coefficient of friction is 0.19 and the push imparts an initial speed of 3.9 meters per second. And this right here, after the pusher stops pushing, is very important. And you can see that I made my diagram a little bit more elaborate than I sometimes do to illustrate a point. We're interested in the motion of the box only after the push has stopped. And so you can imagine that before this picture was drawn, this guy is in the act of pushing. He's in the act of pushing the box, and so he's applying a force to the box. What a lot of people think, though, is that the push that he applied continues to have an effect on the box after he's no longer in contact with it. And this is a huge problem. Okay? Imagine that you were able to apply a force to something without touching it. If you say that this guy's push is still acting on the box after he's no longer in contact with it, even though there's a gap between his hands and the box, then you're really saying that there's something with his hands that's communicating with something in the box. And that's just not really the case. There's no part of him, unless he's got magnets in his hands and there's magnets in the box, that's really going to cause an effective push on this box after he's no longer touching it. And in fact, the distance is what's important here. If you go up to a box and you stand next to it and you put your hands out and you almost touch it, does the box ever move? The answer is probably no. So if you're not able to apply a force to a box by standing next to it and putting your hands close to it, are you able to apply a force to the box after it's already moved away from you? And the answer is no. Now you might be saying, well, doesn't your push have any effect? Your push did have an effect while you were pushing it, while your hands were in contact with it. The box wants to do whatever it was doing just the moment before. When you come up to the box isn't moving. When you start to push the box still wants to not move, which is why you have to apply the force in the first place. Okay? And the more mass of the box, the more it just wants to sit there and do what it was doing before. So the harder you have to push. After you've stopped pushing it, the box wants to continue to do what it was doing the moment before, which was moving. Now you've pushed it and you've gotten up to speed. The box just wants to keep on moving now at the same speed. So you can stop pushing it, and the only effect is that it's not going to get any faster. It's going to want to continue at that same speed, unless acted upon by some other force. In this case, that other force takes the form of friction. Okay, and it's kinetic friction because you're sliding. The surfaces of the table and the box are moving relative to each other. And then all we really have to do is realize that there's a couple of things going on here. We have forces. We know that there's going to be forces involved. There's a force of friction opposing the motion of the box after we have stopped pushing it. Actually, the frictional force is acting against us while we're pushing the box. But we're not really interested in that problem because it says after here, after the pusher has stopped pushing. And we're asked to find how far will the box go. And one thing that should conjure up to you is that we're back in kinematics here. Okay, we're not just talking about forces, we're talking about position and velocities, okay, and accelerations as a result of the forces. So we really need to just try to make this a little bit simpler here. So I'm going to take the box and I'm going to redraw it over here. Actually, that's not very effective. Let me make a box. So just go over this way, and I'll make myself a box. And here we go. So for the force part of this, I'm just going to have, let's call this the force of gravity downwards. Okay, that's one of the forces that's going to be acting, and that's a pretty obvious one. It acts on most things and most of our problems. But in this case, that force isn't that effective because it's being countered by the normal force that the table exerts on the box. Okay? And there's one other force, and that one other force is the force of friction. And that force of friction is going to come back this way. You might be tempted to put some sort of forward force on this box, and I understand why, because the box is going to be moving forward. Right? So there must be some force acting on it if it's moving forward. But that's not true. The box, because of your original pushing, the box is moving forward already. So it's just going to keep on moving forward until friction, until friction acts on it enough to stop it completely. Okay, so we only have the frictional force in the x direction. I'm going to add, just to make things a little clearer, I'm going to make sure that we know that this is the positive direction and this is the negative direction. And for the horizontal motion, I'll make this the negative direction, and I'll make this way the positive direction. Now, because we're not just dealing with forces, I'm also going to do some more labeling over here on my original diagram. I'm going to say that this was the, let's go with the front of the box. So this is the initial position of the box. That's my x initial. And let's say the box slides until it gets to over here, and that I'll call x. The box starts off with an initial velocity, which I'll call v naught, and that's equal to 3.9 meters per second. And we know that when it gets over into here, the final velocity is going to be 0 meters per second. And I just drew a dot there because it's really not going anywhere at that point. So I actually know quite a bit. I'm just going to fill this in at 0 because any number will do. So I have my initial position, I have my initial velocity, I have my final velocity. I'm looking for where does it end up. So I'm only missing a couple of things, and I should be able to get it from over here. So I'm going to list my givens, and I think I might use a nice lilac color for my givens. And I'm going to do this with my kinematics givens. So I have x naught equals 0. X, I'm just going to go down v naught, v a t. X, this is my ultimate question. V naught is 3.9 meters per second. V final is 0. The acceleration, I don't know. And the time, I don't know. And ultimately what I'm looking for here is this guy right here. The problem is that there's no equation that I can use to solve for x without acceleration or time. And this makes perfect sense because if I don't know how long it's moving, I'm not going to be able to find out how far it goes. Or I could get the acceleration and use that. So that's what I'm going to actually focus on, trying to get this acceleration. And the reason why I know I can focus on the acceleration is because we're dealing with forces, and forces also deal with acceleration. So I have that. Then I'm going to look at what are my forces. Sort of a forces subsection. Forces in the x, forces in the y. And in the x direction, I only have one force to worry about. That's the force of friction. In the y direction, I have the normal force, and I have the force of gravity. And it's nice to split them up like this because I can now see clearly that these are my forces in the x, and never do the forces in the x affect what's going on in the y direction, nor vice versa. Alright, so I want to find x. I want to find out how far it goes. In order to do that, I need to find out the acceleration, which I can get if I use forces. So let's start off with a sum of forces in the x direction. Seems like a reasonable way to go about it. So okay, sorry for the interruption. My first step is to do a sum of forces in the x direction, and that's going to equal m times a. I only have the one force acting in the x direction, so I'd set that equal to m times a. Actually, over here, let me just put down coefficient of friction is 0.19, mass. It doesn't appear that I have that. So there's a lot of things that I don't seem to know here. And that's going to get me into trouble over on this side. The force of friction is the opposite of mu times the normal force. In this case, because I designated friction as going in the negative direction, so it must equal some sort of a negative number. Mu is positive, and I'm really just talking about, in this case, what is the absolute value of the normal force times mu. And I set that equal to m times a. I can rearrange this equation and solve for a. So I get a equals the opposite of mu times the normal force divided by m. This is a mess because I don't know this one and I don't know this one. So that's two unknowns aside from the thing I'm actually trying to solve for, which is the acceleration. And this seems like really bad news, except I have another option available to me. I can look in the y direction. So I'm going to do a sum of forces in the y direction. And the reason why I do this is because the y direction is going to tell me what the normal force is like. So the first thing I need to recognize is that in looking in the y direction, the acceleration hopefully is 0. We're not trying to move the box vertically here. So we actually have a pretty simple situation. We have the normal force, and we add to that the force of gravity, and that's going to equal 0. So I get normal force minus mg equals 0. The reason it's minus mg is because I designated it down as the negative direction. And now I can solve for the normal force, and it's equal to m times g. I don't know the actual number for the normal force because I don't know the mass. But what I will get to do is I'll take this and I'll shove it in over here. So now I get that the acceleration equals the opposite of mu times mg divided by m. And we get to cancel out the m's, and we find that the acceleration is really equal to the opposite of mu g, which we could solve for if we wanted to, but I'm not terribly interested in that right now. I'm going to go ahead and do the final step, which is to deal with finding the change in position. So now I know what the acceleration is. The only thing that I don't have and don't know and don't care about is time, which means I'm going to use the no-t equation. Okay? One of the nice features here is that this is going to be 0. The final velocity is going to be 0 because we're looking to see how far it goes, period. And it'll keep going forward until it comes to a stop. At no point is it going to turn around and come backwards. So I set the final velocity equal to 0, and now I have 0 equals v naught squared plus 2, and then my a is equal to the opposite of mu. It's actually not a very good mu. The opposite of mu times g times x, because I can actually do delta x as x minus x naught, but x naught I set equal to 0. So now all I have to do is do a little bit of rearranging here. So I get the opposite of v naught squared equals 2 times the opposite of mu g x. And I'm going to change colors because those colors are actually a little bit boring. One of the things that I notice here is the negative signs are going to cancel out. And now I get v naught squared divided by 2 mu g equals x. I plug in my numbers, which would be 3.9 squared divided by 2 times 0.19 times 9.8. And I find, if I do a quick calculation, that the answer is 4.1 meters, about. So to just briefly summarize, because I know this is getting to be quite long, we had to look at the kinematics version of the problem, we had to look at the forces version of the problem, and I broke up my givens, I split my forces into the x and y, I tried to solve for the acceleration, which I knew I was going to need to get another variable to help me solve for x. That failed. I was left with not knowing the normal force, so I had to go into the y direction to figure out what the normal force was, plug that back in, got my acceleration. Then I could do a kinematics formula and solve. One of the big conceptual things with this, though, was that a lot of people would tend to think that because this person was pushing on the box originally, that push is still having an effect. Not so. The box is going to continue doing what the last thing you told it to do was, which is, in this case, move forward at 3.9 meters per second, until it's acted upon by an outside force. In this case, there is an outside force that's going to affect its motion immediately and continuously, and that's the force of friction. But your push, the force with which you pushed, no longer plays any role in this problem as soon as you're done. And that's it for this problem.